Welcome students to MOOC's lecture series on advanced probability theory. This is lecture number 24. As I said, from this lecture I shall start convergence of random variables. In analysis, we have studied convergence of a sequence of numbers x n. We say that x I converges to some number if given any epsilon greater than 0, there exists n such that for all n greater than equal to n, modulus of x minus x n is less than epsilon. That is, after some finitely many members of the sequence, all the remaining ones will be within the epsilon neighborhood of x. This is what all of us know, I assume. The question is, what happens if we consider a sequence of random variables we have already seen sequence of random variables such as, say, a coin is being tossed n number of times and let x 1, x 2 up to x n denote the sequence of random variables denoting each individual outcome. Since these are random variables, each x I takes values, in this case only two possible values, namely 0 and 1, each with certain probabilities. Hence, it needs a different treatment as opposed to numbers. I hope the concept is clear. So, we have x 1, x 2, x n, a sequence of random variables. Each random variable can take a set of values depending upon its omega, each one with certain probability. Then, what do we want to see is where the sequence of random variable actually converges to. So, let me give an example. Consider x 1, x 2, x n such that each x I takes two values as follows. X I takes only 0 and 1 with probabilities half minus 1 upon I plus 1 and half plus 1 upon I plus 1. So, this is the probability mass function for x I. Note x 1 therefore takes values 0 with probability 0 and 1 with probability 1. That is, it is a degenerate variable. And not of any interest for the long run. What about x 2? X 2 takes values 0 with half minus 1 by 3 and 1 with half plus 1 by 3, that is, it is equal to 1 by 6 and this is equal to 5 by 6. What about x 3? X 3 takes 0 with half minus 1 by 4 is equal to 1 by 4 and 1 with probability half plus 1 by 4 is equal to 3 by 4. Like that, we can compute the PMF for each x I greater than equal to 1. Question is, what happens if n goes to infinity? Now, PMF for x n is, it takes 0 with probability half minus 1 upon n plus 1 and 1 with probability half plus 1 upon n plus 1. Therefore, as n goes to infinity, probability x n is equal to 0, that goes to limit n going to infinity half minus 1 upon n plus 1 is equal to half, and probability x n is equal to 1, that converges to limit n going to infinity half plus 1 upon n plus 1 is equal to half. Thus, limit n going to infinity of x n is a Bernoulli random variable with parameter is equal to half. Let us consider another example. Suppose x 1, x 2, x n is a sequence of independent and identically distributed random variables such that each x I takes two values, 0 with probability 1 minus p and 1 with probability p. Now, let us consider a new sequence of random variables S n defined as follows. S n is equal to x 1 plus x 2 plus x n by n, that is S 1 is equal to x 1, S 2 is equal to x 1 plus x 2 plus 2, S 3 is equal to x 1 plus x 2 plus x 3 by 3, S k is equal to x 1 plus x 2 plus x k by k, like that. Question is, what happens as n goes to infinity? That is, what is the long term behavior of S n is equal to x 1 plus x 2 plus x n upon n. We know that x 1 plus x 2 plus x n is distributed as binomial with n p. Therefore, expected value of S n is equal to expected value of sigma x I is equal to 1 to n divided by n is equal to 1 by n expected value of binomial n comma p is equal to n p upon n is equal to p. Also note that variance of S n is equal to 1 by n square into variance of sigma x I is equal to 1 to n is equal to n p q upon n square is equal to p q by n. Therefore, as n goes to infinity, variance of Sn converges to 0. Therefore, Sn converges to its expectation, that is, the sequence Sn converges to the constant P, which is the unknown probability of success of the parameter of the Bernoulli random variables xi. Thus, we find the following. In case 1, xn converges to a random variable. In case 2, xn converges to a constant, which is p. Thus, convergence of a sequence of random variables may take different forms. Hence, there are different ways of defining the convergence of a sequence of random variables, or in other words, we call it different modes of convergence. So, in these lectures, we shall study a few of the different modes of convergence for a sequence of random variables. One of the weakest form of convergence is called convergence in distribution or convergence in law. To understand that, let us first consider a sequence Fn of distribution functions. If there exists a distribution function f such that f n x converges to f x for all x belonging to R, where f x is continuous, then f n is said to converge to f weakly. That is, it is a weak form of convergence of the distribution functions. Now, consider x n to be a sequence of random variables such that the distribution function of x n is f n. Then, if f n converges to f weakly, we say x n converges to a random variable x whose distribution function is f. Note, a sequence of distribution functions f n converges to a function f does not necessarily mean that f itself is a distribution function. Therefore, in such a case, even though f n converges to f, we cannot say x n converges to some random variable x. So, this is one point that you have to understand. So, I shall give you examples, so that this is going to be clear to you. Example 1, let x 1, x 2, x n be a sequence of random variables with the following distribution. X n is equal to 0 with probability 1 minus 1 by n, and n with probability (1 by n). So, how do they look like? So, x 1 takes the values 0 with probability 0, and 1 with probability is equal to 1. X 2 takes 0 with probability is equal to half, and it takes the value 2 with probability is equal to half. So, let us consider x 3, which takes the value 0 with probability 2 by 3, and it takes the value 1 with probability 1 by 3. Therefore, we observe that as n increases, probability x n is equal to 0 converges to 1, and probability x n is equal to n converges to 0, and of course, probability x n is equal to k, k not equal to 0 or n is equal to 0. So, let us consider their distribution functions. So, let us assume 0, 1, 2, 3, n. So, what is the distribution function for x 1? It takes the value 0 with probability 0, and it takes the value 1 with probability 1. So, if this is the value 1, then the distribution function of x 1 is going to be something like this. What about x 2? X 2 takes the value 0 and 2 with half and half. So, if this is my half, after 0, the cumulative distribution function goes to half, and at 2 it goes to 1, and it remains 1 throughout. So, this is for x 2, this is for x 1. What about x 3? X 3 takes the value 0 with probability 2 by 3, and it takes the value 3 with 1 by 3. Therefore, its distribution function will be something like this. Therefore, what is going to happen? If that is the question, we can understand that it will take the value 1 minus 1 by n and go up to n, and then at n it becomes 1. Therefore, as n goes to infinity, if n at 0 is converging to 1 and therefore, for all x greater than 0, f n x is going to be converging to 1 and f n x is 0 for all x less than 0. Therefore, we see that x n converges to a variable x which is degenerate at 0. Example 2, let x 1, x 2, x n be IID random variables with uniform 0 theta. That is, f n of x is equal to 0 if x less than 0 or x greater than theta, and is equal to 1 by theta if 0 less than equal to x less than equal to theta. Let y n be defined as y n is equal to maximum of x 1, x 2, x n. Therefore, y n has the following distribution function, that is, f n is equal to 0 if x less than 0, x by theta whole to the power n if 0 less than equal to x less than equal to theta, and 1 if x is greater than theta. Now, for all x such that 0 less than equal to x less than theta, it is strictly less than x by theta is less than 1. Therefore, x by theta whole to the power n goes to 0 as n goes to infinity. Therefore, f n, that is distribution function of cumulative distribution function, you can say, of y n converges to 0 if x less than theta and 1 if x is greater than equal to theta. That means, y n converges to the random variable, say y, which takes the value theta with probability is equal to 1. Example 3, consider a sequence of random variables x n such that x n is equal to 0 if x is less than n and 1 if x is greater than equal to n. Therefore, x 1 is equal to 0 if x less than 1 and is equal to 1 if x greater than equal to 1. Therefore, x 2 is equal to 0 if x less than 2 and 1 if x greater than equal to 2. X 3 is equal to 0 if x less than 3 and it is equal to 1 if x greater than equal to 3. Therefore, if we denote f I to be the distribution function of x I, we have the PDF of, we have the distribution function of x 1 is equal to 0 if x is less than 1 and 1 if x is 1. For x 2 we have it is 0 till this point and at 2 it takes the value 1 and it remains there after that. X 3 will remain at 0 till 3 and at 3 it will take the value 1. Therefore, as n goes to infinity, f n at x goes to 0 for all x, because given any x belonging to R, there exists n such that n is bigger than x. Therefore, for all n greater than equal to n, f n x is equal to 0. Therefore, f n x converges to a function f which is 0 everywhere. Thus, f n x does not converge to any distribution function f as mentioned earlier. Now, let me give you a theorem. Let x n be a sequence of integer valued random variables such that Fn k is equal to probability xn is equal to k, when k is equal to 0, 1, 2 up to infinity. Suppose Fn x converges to Fx for all x. This implies that Xn is converging by law to the random variable x, which has the PMF Fx. Proof. Let us first observe the following. Xi has the distribution Xi takes the value 0, 1, 2, 3, n, etc. with probabilities Fi 0, Fi 1, Fi 2, Fi 3, Fi n, like that. Similarly, x takes the same values 0, 1, 2, 3, n with probabilities f0, f1, f2, f3, fn, like that. Therefore, distribution function for x is Fx is equal to 0 if x less than 0, it is f0 if 0 less than equal to x less than equal to 1 less than 1, f0 plus f1 if 1 less than equal to x less than 2, sigma fi I is equal to 0 to k if k less than equal to x less than k plus 1, like that. Therefore, it is a step function. Now, it is given that Fn k converges to Fk for all k is equal to 0, 1, 2, etc. Therefore, consider x less than 0. Therefore, trivially Fn x is equal to 0 for all x. Therefore, Fn x converges to Fx. 2. Consider 0 less than x less than equal to x less than 1. Therefore, f n x is equal to f n 0, which converges to f 0, which is equal to f at 0. Similarly, consider 1 less than equal to x less than 2. Therefore, f n x is equal to f n 0 plus f n 1, and we know that if a n converges to A and B n converges to B, then A n plus B n converges to A plus B. So, this we know from our high school mathematics. Therefore, f n x converges to f 0 plus f 1, which is equal to f at x when 0 less than equal to x less than 1. In a similar way, we can show that f n x converges to f x for all points of continuity of f x. Thus, we see that if f n x converges to f x, x is equal to 0, 1, 2, etc., then this sequence of random variables x n converges in law to the random variable x with PMF is equal to f x. So, I want you to remember this notation. So, notation for convergence in distribution is x n convergence in distribution in log or x n, that is we are using the symbol L to denote that it is a convergence in distribution. Now, there is a converse part of it, that is if x n converges to x in distribution, then for all x, f n x converges to f x. This we shall prove in the next class. Okay, friend. Thank you so much. Thank you.